For this problem, let's study whether or not this series converges or diverges. Summation n equals 1 to infinity, 1 over n plus 1 to the nth power. There are at least three different ways of doing this problem, two of which are actually pretty good. Method number one. Well, I've got an nth power here, so that gives me a tip-off that maybe I should try the root test. So let's use the root test. Limit as n goes to infinity of 1 over n plus 1 to the n, whole thing to the 1 over n power. That's equal to the limit as n goes to infinity of 1 over n plus 1 to the n to the 1 over n. Now, by the laws of exponents, I can multiply these two together, and I get the limit as n goes to infinity of 1 over n plus 1 to the first. And clearly, this is 1 over something that blows up, and so that'll be equal to 0. So I get either 0 or a number that is less than 1, and so therefore, the series converges by the root test. Okay, so that is one way of doing the problem, and that's the way that, honestly, I'd probably expect a student to do this problem. There are at least two other ways of doing the problem, and so let me show you how these go. Method number two is we use the comparison test. If n is greater than or equal to 2, then let's take a look at 1 over n plus 1 to the nth power. That is going to be less than or equal to 1 over n plus 1 squared, right? I'm going to make the denominator smaller. Instead of taking an nth power, I'm only going to square it because n is greater than or equal to 2, I'm taking a lesser power. And I've got a number here that's bigger than 1, so I know that's making it smaller. Now, I'll further make the denominator smaller by replacing n plus 1 by n. So I've made the denominator smaller again, but still positive, and so that makes the fraction bigger. Okay, so since summation 1 over n squared converges, and the reason that converges, it's a p-series with p is equal to 2, which is greater than 1, we conclude that the original series converges by the comparison test. Okay, and so that is a second way of doing the problem. I wouldn't necessarily expect you to do the problem like this, but it's pretty quick. You compare this series to this series, which converges. Method number three is definitely the most work, and I definitely would not expect anybody to do this on an exam. However, because we're reviewing for the exam, I'm more than happy to kind of do this just for the sake of practice so we can see how this works. Let's use the ratio test. Okay, so we get the limit as n approaches infinity of 1 over n plus 2 to the n plus 1 all over 1 over n plus 1 to the n. Okay, now that's a bit of a mess. Limit as n approaches infinity of n plus 1 to the n over n plus 2 to the n plus 1. Okay, let's rewrite the fraction as n plus 1 over n plus 1 to the n over n plus 2 to the n times an extra 1 over n plus 2. Okay, so we get, let's see. What do we have here? We have limit as n approaches infinity of n plus 1 over n plus 2 to the nth power times 1 over n plus 2. Now, I can evaluate this. It turns out the answer is 1 over e. But the important thing for the purpose of this problem is that this fraction here is less than 1. So that's less than or equal to the limit as n approaches infinity, 1 to the n times 1 over n plus 2. This fraction is less than 1. The numerator is strictly less than the denominator. Now, 1 to the n is always 1, and as n goes to infinity, that goes to 0. And so we conclude that the limit as n approaches infinity of a sub n plus 1 over a sub n is equal to 0. This limit is positive, or it's non-negative. It's less than or equal to 0. The only way that happens is if the limit is equal to 0. And therefore, because this limit is equal to 0, therefore the series converges. By the ratio test. Okay, and so I certainly would not expect anybody to do the problem this way, but it can work with the ratio test. For this one, however, I would probably recommend the root test.